Hello everyone. Thanks for watching this presentation. My name is Reza Ghaffari Bardawagh and I'm a research scientist at MIT. Today I'm going to talk about our research on scalable and ultra-low power Internet of Things for the ocean. This is a joint work with my colleagues Saad, Ozvi, and Fadl. There is a significant interest in ocean IoT due to its huge potentials. For example, we can use it for ocean exploration. Unfortunately, according to NOAA, as of 2018, more than 80% of the ocean remain unobserved and unexplored. Ocean IoT allows us to deploy sensors and have them transmit back their information to us so that we can expand our understanding of the ocean. Ocean IoT has also application in underwater climate monitoring. According to National Geographic, in 30 years, coral reef could be gone due to the bleaching. It is extremely important to monitor them now because they are a fundamental part of the health of our planet and its ecosystems. With Ocean IoT, we can build a technology that can image coral reef and monitor them over time and extract the information and send it to us using Internet of Things. Finally, Ocean IoT can transform aquaculture industry. Named as the fastest growing food sector by United Nations Food and Agriculture Organization, aquaculture is projected to scale over the next decade to fill the gap between the increased need for nutrition and depleting resources. With Ocean IoT, we can optimize aquaculture. We can monitor environment to prevent any health hazard that can affect our food chain. Unfortunately, the existing technologies are not amenable to deliver on these applications. Broadly speaking, the current underwater communication technologies falls in two categories. In a conventional form of underwater communication, let's say we have a sensor that wants to transmit its information to a remote receiver. The way that sensor does this is it's equipped by the speaker, and on the receiver side, we have a hydrophone. Now, to send out the information, sensors generate an acoustic signal that will be picked up by the hydrophone on the receiver side. For those of you who are not familiar, we cannot use Bluetooth or Wi-Fi in underwater because these signals decay very rapidly in water. Now, the nice thing about this approach is with this approach we can get sufficient throughput of about 10 to 50 kilobits per second to deliver on the vision of Ocean IoT. We can also communicate over a long range that can be about 50 to 100 meters or even more. But the problem, however, with this approach is generating acoustic signal consumes a lot of power. And if the sensor has a battery, it will drain the battery very fast. And what you need to do is to go out, replace the battery, and come back. But unfortunately, this is very costly. In fact, a research vessel costs around $50,000 a day to operate. And this approach becomes very costly to scale. To address these issues, our group last year came up with a new form of underwater communication called Backscatter. In this approach, both speaker and hydrophone are shifted to one privileged side that can be near the shore, and the sensor is equipped with the acoustic reflector. Now, to communicate, the sensor, instead of generating its own acoustic signal, modulates the signal already exists in the environment. In a simplest form, simply by choosing reflecting and not reflecting, sensor can transmit bits of zeros and one, and we can transmit any information. Now, in this approach, because the sensor does not need to generate its acoustic signal, it is ultra low power, and in fact, we can even design completely battery-less sensor. And it becomes very cost efficient to scale. But what we observe with this approach is we can only achieve the communication with a very limited throughput of about 2 to 3 kilobits per second, which limits us significantly to enable many applications. Additionally, we were only able to communicate over a short range of about 5 to 10 meters. In this talk, I will tell you how we can get the best of both worlds and we can design a system that can give us ultra low power and cost efficient communication while having a sufficient throughput over a long range. I will be telling you about the technology that we build, which is called ultra wideband underwater backscatter, or in a short form U2B. U2B is the first technology that enables scalable ultra low power and low cost ocean IoT. Additionally, we introduced a novel metamaterial design for underwater backscatter that enabled us to communicate with a higher throughput over a longer range while maintaining the low power and low cost of the backscatter. This is also the first demonstration of underwater backscatter in the wild. We performed our experiment in the river across different weather conditions such as snow and rain. Now, before explaining more about this technology, I would like to first tell you why our period design was limited in throughput. The main problem that we had to face is underwater backscatter exploit resonant material, which limits their throughput. Let me explain to you what I mean by this. Recall that in underwater backscatter communication, we use acoustic reflector to modulate the reflection and communicate. At the heart of our acoustic reflector, we are using what is called piezoelectric material. Indeed, the way that we controlled the reflection was by tuning the vibration of this element. Now, the problem is, while controlling the reflection to communicate relies on tuning the vibration of the piezo itself can only vibrate at its resonance frequency. So, for those of you who are not familiar with what is resonance frequency, let me give you an example. You can think of it as a guitar and a string of the guitar. I don't have a guitar here, but this is a string-based instrument. And if I plug any of these wires, you will see it and you will hear a different sound. The reason is each of these wires, they have a different resonance frequency. And when I plug them, they tend to vibrate at their resonance frequency. So similar to the string of the guitar, the piezo tends to only vibrate around its resonance frequency. And the problem with the resonance is it is very narrow bandwidth. If you take a piezo with the resonance frequency of, for example, 20 kilohertz, and if you plot the amplitude of the vibration of this piezo, what you will get will look like this. And as a result, you will only get the signal around 20 kilohertz, which is very narrow bandwidth. The conclusion here is the resonance of the piezo is narrow bandwidth, and as a result, the communication with this element becomes very limited in throughput. The Strawman solution to this problem is to stack many piezos, each at different frequency, and connect them together. Let's say we want to communicate at 20 kHz. Then we can simply take a piezo and use it with the resonance at 20 kHz. Now, if I want to be able to also communicate at 21 kHz, I can simply add another piezo with a resonance at 21 kHz, and so on and so forth. With this approach, yes, we can get a wideband and high throughput communication. But this approach is really problematic in many reasons. First, it's very costly. With this approach, the cost of each sensor would be multiplied by 10 to 100. Also, it leads to a very bulky solution. And importantly, the array of these piezos will generate unwanted directionality, and we may focus the reflection to a specific point, and we may not be able to communicate anywhere around us. So this approach is really undesirable and defeats the purpose of low power, low cost, scalable ocean IoT. And what we wanted is to come up with a solution that does not suffer from these problems. So the question we asked ourselves was how we can then overcome the resonance problem while maintaining low cost and low power of underwater backscatter. The answer that we have for this question was by introducing a novel metamaterial design that enabled us to achieve ultra-wideband backscatter. Metamaterials are man-made structures that can give us the properties that are not found in nature materials. So instead of limiting myself to the resonance of the guitar string or a simple piezo, I can design a new material that can give me a wide resonance. In the rest of this talk, I will tell you how we designed such metamaterial structure and how we evaluated that leads to boosting our throughput and range. The key idea was to create a coupling between only two piezos, and with this coupling, we were able to synthesize many more resonances. Let me explain to you what I mean by this. So what we did was we took one piezo, which is shown in yellow, with a resonance frequency at 20 kHz. And we took another one shown in blue with a resonance frequency at 40 kHz. And we placed the smaller piezo inside the larger one. Then we filled the spacing between two piezo using polymer, which is a soft material. Now, if we take a look at the vibration profile of the structure, what's interesting is because polymer is very soft compared to the piezo, the resonance of each of those individual piezos will be reflected in the vibration of the entire structure. So if we take a look at the amplitude of the vibration for this structure, we will see the one resonance corresponding to the first piezo and another resonance corresponding to the second piezo. But now, because we define a polymer between those two piezos, which creates a constraint on the movement of those piezos, this constraint leads to generation of new form of vibration and resonances that fill the gaps between these two main resonances. And as a result, we can get a structure with a wideband vibration. Now, let me explain to you visually what is happening in this structure, which can give us a wideband resonance. So if I take one frequency like this one, which is closer to the resonance of the first piezo at 20 kHz, this is how the structure would look like at this frequency. The heat map I'm using here, red indicates the high intensity vibration and blue indicates low intensity vibration. In this mode of resonance, we can see that the outer piezo is vibrating strongly while the inner one does not have a strong vibration. Now instead, if I take another frequency more closer to the resonance of the second piezo, we will get this one, which you can see the inner piezo is now vibrating very strong and outer piezo does not have that level of strong vibration. Now instead of taking these two extremes, if I take a frequency in between, we will get a completely different mode of the vibration, which is generated due to the coupling between the vibration of these piezos. In this mode, for instance, the edge of both of these piezos are vibrating strongly. And this mode is generated because of the constraint that we define between them. Now, if I take another one, we can get a completely different mode of vibration. And it's very interesting. It almost looks like the inner piezo is split into half and is vibrating very strongly, while the outer one is relatively stationary. And this is possible only by the constraint and the coupling that we generated in this structure. Now, I explained these modes at a very high level now, but indeed these modes and these many resonances can be derived as a solution of the differential equation, which is shown here in the form of determinant equation. And in this determinant equation, omega represents frequency, m is a mass tensor, and k is elasticity tensor. In the interest of time, I will not get into the details of this equation, but I would like to invite you to read the paper to know more details about this equation and why it leads to these many different modes of the resonance. Now, the conclusion here is with U²B metamaterial design, we were able to enable the resonance bottleneck and we were able to achieve ultra-wideband operation. Up to this point, I have told you how we can achieve ultra-wideband backscatter. And it is straightforward to see how we can go from wideband to high throughput, which is simply by backscattering at a higher rate. What is less clear is how we can use this structure to achieve longer range. In the next part of this talk, I will tell you how we can use this structure to achieve longer range communication. But before that, let me quickly explain to you why our period design was limited in range. The main factor limiting the underwater backscatter communication range is self-interference. Recall that in underwater communication, we relied on modulating the reflecting signal to communicate. But this is not the only signal that will be picked up by the hydrophone. In fact, we have another signal which goes directly from transmitter to the hydrophone, and it has a much stronger amplitude compared to the backscatter signal that has gone all the way to the backscatter node, reflect, and then receive back to the receiver. And because of the presence of such strong signal, what it will do, that it will overwhelm the receiver, and we won't be able to differentiate and detect the backscatter signal. The way that ultra-wideband node can help us is ultra-wideband node enables reflecting the signal at a different frequency. Let's assume that we transmit the signal at 20 kHz. Now, both incoming signal to the node and to the receiver from direct pass, they have the frequency of 20 kHz. Now, relying on the wideband node, it can backscatter at a higher rate and it can modulate the signal on top of that 20 kHz. So let's say if the node can backscatter at 20 kHz, then the reflected signal to the receiver will have the frequency of 20 plus 20 or 40 kHz. And in this case, to enable detection of this tiny backscatter signal, the only thing that receiver needs to do is to apply a high-pass filter to remove the signal with the 20 kHz. And because of that, it can decode the backscatter reflection from far away node. The conclusion here is, using ultra-wideband node, we can do out of backscatter, and then we can filter direct pass signal that enabled U²B to extend the communication range. Now, let me tell you how we implement and fabricate our prototype. To fabricate our structure, as I mentioned earlier, our node is composed of 3 layers. We have one piezo in the outside with the center frequency of 20 kHz. Inner piezo has the resonance of around 40 kHz, and we built these 2 piezo ceramic transducer from stemming. And for polymer, we use 2-part polymer solution from BJB Enterprise, and we mixed it and we created inside the lab. After this, we 3D printed 2 caps for the structure, and we laser cut washers on top of these caps. And we assembled the whole structure using a screw and nut and tighten it. Eventually, we encapsulated the whole structure with a polyurethane polymer, and we let it to be cured overnight under a high pressure inside the pressure chamber. And that's the finalized U2B node that we were able to fabricate. For our evaluation, we performed our experiment in the charged river in different weather conditions, such as snow and rain. And also, we used hydrophone resin TC4014 to receive the signal, and this hydrophone was connected to the USRP software radio, and at the end we demodulate the signal and decode this FM0 in MATLAB. In total, we ran over 400 experimental trials at different range, throughput, and number of the node. Now, I want to just present you 2 of our main results. And for the rest of the result, I would like to invite you to read the paper. The first result is about throughput. The experiment we did here was we changed the backscatter rate and we tried to decode the signal. So here what I'm going to show you here is on x-axis I do have the backscatter bitrate, and on y-axis I'm showing signal to noise ratio. For underwater communication, the threshold usually is defined as a bit error rate of 10 to the power of -2. So I'm going to use this threshold to evaluate my throughput. Now let's first take a look at how our period system will perform. In this system, you can see that the SNR goes lower than the threshold that we have, as low as about 4 kilobits per second. And if you're lucky, you may get something at 5. But generally, with this design, the throughput is limited in the range of 3 to 5 kilobits per second. But now, using the U2B design, if we test its throughput, this is what we will get. So we can see that the SNR of U2B remains well above the threshold up to about 20 kilobits per second. That can enable us to do many more applications such as streaming image or even low quality videos. Now, the conclusion here is with U2B and due to its ultra wideband nature, we were able to boost throughput by about 5 times over the state-of-the-art system. Now I will show you how we were able to extend the range. The experiment we performed was we changed the distance between the backscatter node and the co-located transmitter and hydrophone. What I'm going to show you is on x-axis I'm showing the distance in meter, and on y-axis I'm having signal to noise ratio. I want you to remind that with our period design we were able to only achieve up to about 10 meters of communication. Now with U2B, this is the SNR that we will get over distances. And now you can see that with this new design and by performing out-of-band backscatter, we were able to significantly boost the communication range to about 64 meters. The conclusion here is with U2B and out-of-band backscatter, we were able to boost communication range by about 6 times over state-of-the-art system. As a conclusion, I told you today about our major leap on designing ultra-low power and scalable ocean IoT. I also told you about our design based on Metamaterials that help us to significantly boost the throughput and the range. And with this advancement, now there are many more applications and possibilities ahead of us in different areas ranging from ocean exploration to climate monitoring to food safety. We are very much enjoying working on this project, and we would like to invite you to join us in this exciting journey. We are releasing a lot of tutorials or code on how to fabricate and how to evaluate those 101 instructions, and I would like to invite you to explore it and join us in this very exciting journey. Thank you.